Hello everyone, my name is Ned Dimitrov, and today I'll tell you about an optimal cover time for a graph-based coupon collector process, which is joint work with Greg Plaxton at the University of Texas at Austin and was presented in iCalp 2005. Let me begin by reviewing the classic coupon collector process. A way to view this process is that originally we're given a graph with n nodes and no edges, and we proceed in rounds where in each round we select a uniformly random node u and cover it. It's well known that this process, without replacement, has a cover time of n, which means that it takes n rounds to cover the entire graph. And with replacement, it takes theta n log n rounds to cover the entire graph. In today's talk, we're going to look at a generalization of this that's called the graph-based coupon collector process. And in general, this process looks like this. Again, we're given a graph with n nodes, but this time it could have some edges. And we proceed in rounds, where in each round we select a uniformly random node u and cover an uncovered neighbor of u. Now, of course, the way that we choose the uncovered neighbor leads to different instantiations of the graph-based coupon collector process. So in today's talk, we're going to talk specifically about one such instantiation. So in this instantiation, originally we're given a theta log n degree graph with n nodes. And at the beginning of the process, each node selects a uniformly random rank between 1 and log n. Then we proceed in rounds, where in each round we select a uniformly random node from the graph u, and then we cover a minimum rank uncovered neighbor of the selected node. So let's go through an example of this just to make sure that everybody understands. So on the right here, you'll see our example graph. So initially, as the process begins, each node selects a uniformly random rank between 1 and log n. And then we start the rounds. So in each round, we first select a uniformly random node from the graph, and then we look at the minimum rank uncovered neighbor of u, and that's the node which we cover. So in this case, the minimum rank uncovered neighbor of the selected node is this top node with rank 2. So that is the one that we cover. So let's proceed again to the next round. We select a uniformly random node. It could be one of the cover nodes. We looked at all of the neighbors, and then we cover the minimum rank neighbor. So the minimum rank neighbor in this case is the neighbor with rank 1. We do it again. We select a uniformly random node. It could be a node that we've selected before. We once again look at the uncovered neighbors, and we select the minimum rank neighbor. Now, there's a tie here, and we're just going to break ties arbitrarily. So let's proceed for a couple of more rounds. Now, we could have a selection where all of the neighbors are covered. And in this case, we simply don't get to cover any node in this round, and we have to move on. So the question is this process as fast as covering the graph without replacement up to constant factors? In other words, do we have a linear cover time for this graph-based coupon collector process, the same as we did for the original process without replacement? This process has been studied on expanders by Alone, and he showed that on log n regular expanders it has a linear cover time. Also, he showed a general lower bound for theta d degree graphs. So he showed that for theta d degree graphs, it takes at least n log n over d time to cover the graph. Adler, Halperin, Karp, and Vazirani studied the graph-based coupon collector process on the hypercube, and they showed that it has a linear cover time on the hypercube. In addition, they showed n times log n bound for arbitrary theta log n degree graphs. And they also show an application of the graph-based coupon collector process to load balancing in distributed hash tables. In our paper, we show a linear cover time for arbitrary theta log n degree graphs. And in addition, we have a bound that matches Alone's lower bound for theta d degree graphs. Our approach is significantly different than the approaches in the previous two papers. So for example, our approach uses absolutely no graph structure except the degree bounds, while both the previous papers use some kind of expansion property. Alone used expansion properties of expanders, and Adler, Halperin, Karp, and Vazirani used some expansion-like properties for the hypercube. In addition, what lets us do this proof without the use of graph structure is that we use what's called a delay sequence argument. And this argument structure or argument skeleton was originally developed by Upfall in 1981, and there was also famous application of it by Ranaday in 91 to routing in the butterfly. So let's see what a delay sequence argument looks like. So our goal is to show that some random process, pi, and r here is the randomness of the random process. We want to show that this ends in some small amount of time. So big O of some t of n. So here are the steps to the delay sequence argument. First, we identify a set of combinatorial objects we call delay sequences. After we define these objects, we're going to hook up each object to a specific time in the process, and we do this by defining the notion of an I-active delay sequence. So I is going to be a particular round in the process. Then we're going to argue that a process ending in round j creates a j-active sequence. Then we use probabilistic arguments to show that the probability there exists a longer than t of n active sequence is very small, and all of these arguments let us conclude that the process ends quickly with high probability. So let's see how we're going to apply this to our graph-based coupon collector process. So here's the intuition. The first thing that we have to do, remember, is sort of have this definition of a delay sequence object. So here's the intuition. Imagine a completely covered graph at the end of the process. And let's think about the node that got covered on the very last round. So on the very last round, we selected some node SL. And we covered some node CL. And one question that we could ask is, why didn't we cover this final node CL earlier? Well, let's backtrack through time for a little bit. And perhaps we had a previous opportunity to cover CL when we selected SL-1. But instead of covering CL, we covered some other node, CL-1. So CL was delayed by CL-1 in this case. So let's backtrack through time once again and ask the question, why didn't we cover CL-1 earlier? Well, once again, perhaps we had an opportunity to cover CL-1, but instead we covered another node, CL-2. So CL-1 was delayed by CL-2. And we're going to keep doing this until we get to a node which we cover on the very first opportunity. In other words, this node wasn't delayed by anyone. So our intuition leads us to define delay sequences to be a path of pairs like this. A selection node S1 and a covering node C1, then a selection node S2 and a covering node C2, where we have these delays. So we've completed the first part of the delay sequence argument, identifying objects called delay sequences. Now we can move to the next part, which is that we have to hook up each delay sequence to a particular round in the process. So we have to define this notion of an I-active delay sequence. So here's the intuition. What happened to make this delay sequence occur? In other words, what are the probabilistic events that must have happened for all of the delays to happen in such a sequence? Well, one of the things that must have happened is that the ranks must be ordered. In other words, CL-1 must have a less than or equal to rank to CL, and so forth. So all of the ranks must be ordered like this. The second thing that must have happened is each Cj must have been covered by selecting the node Sj. And the final thing that must have happened is that C1 was covered on the very first chance, and Cj was covered on the very first chance after we covered Cj-1. So here's our first try at defining an I-active delay sequence. So delay sequence, remember, is a path of pairs like this, and we're going to call such a path of length L an L sequence. So then we're going to try to define an I-active delay sequence as follows. First of all, the first thing that must happen is all of the ranks must be sorted. The second thing that must happen is each node Cj must be covered by selecting the corresponding node Sj. And the final thing that must happen is C1 is covered the first chance, and Cj is covered the first chance after Cj minus 1, and finally Cl is covered in round I. Now, you might be wondering, are these events independent? Like, for example, if we know that Cl is covered in round I, then maybe we have some information that the rank is rather large, and so we don't really have independence here, which is going to make our analysis difficult. So let's try to fix up our definition so that we can actually analyze it by using independence. So what we're going to do is concentrate on this last requirement here of the nodes getting covered on a first chance after some other event. And we're going to redefine that in a more precise way. So the way that we're going to do this is by introducing another definition that's called the duration of a particular L sequence. So let T1 be the number of rounds before hitting the neighborhood of C1, remember that's the very first node in the sequence, after the beginning of the process. We'll let Tj be the number of rounds before hitting the neighborhood of Cj after round Tj minus 1. Remember, this is a random variable that's defined recursively. And the duration of the entire L sequence is going to be the sum of these random variables. Each of these random variables is a geometric random variable because we're simply flipping a coin or waiting until we hit the neighborhood. So in other words, it's the number of flips or the number of turns before we get a success. So the sum of these geometric random variables is a negative binomial random variable. So that's the duration. So we're going to fix up our definition of an I-active L sequence as follows. Again, we're going to require that the ranks are sorted. We're going to require that Cj is covered by selecting Sj. And the last requirement is going to be that the L sequence has duration exactly equal to I. So this completes the second part of the delay sequence argument, where we have to define the notion of an I-active delay sequence. The next part is that we have to argue that a process ending in round J creates a J-active sequence. But we already argued this in my intuition slide where we came up with our notion of delay sequence. So for our argument, this part is easy. So the really difficult mathematical part is to show that the probability there exists a long active delay sequence is small, or rather there exists an omega t of n active delay sequence is small. So let's see how we're going to go through this probabilistic reasoning for our particular analysis. Now each of these events, A, B, and D, has some probability associated with it. In particular, the probability of D is just the probability that a negative binomial random variable is equal to I. Another thing we can do is actually go through and argue that each of these three events is independent. So just to give you a loose intuition of this, the first event only depends on the ranks of the nodes in the graph. The second event only depends on where a selection happens. And the third event only has to do with when a particular selection happens. So the probability of a particular L sequence is I-active is going to be the multiple of these three probabilities. And what we have to show is that no long or no omega t of n active sequence exists. So here's the first part. What we're going to do is sum over L sequences. So the lemma that we're going to use is that there are not many L sequences because they just correspond to paths in the graph. And there can't be very many repeated nodes because each of the C nodes get covered. So we can get the probability that any L sequence is I-active is less than or equal to the number of paths of length L, or about the number of paths of length L, times the multiple of these three probabilities. So remember that our goal is to show that there isn't an I-active sequence very late in the process. So we're going to have to sum both over L and over I, and this lemma that gives us the probability that any L sequence is I-active. So what we're going to want to do is sum over all i's that are bigger than a constant times n, and we're going to split the analysis into two cases. So first we're going to consider a very large values of L. Well, in this case, the first two terms, the probability of A times the probability of B, is going to be very small. So why is this? Well, for very large values of L, it means that the sequence is very long. So that means that we have to have many, many sorted ranks, and the probability of this would be small. In the second case, we have small values of L. Well, in this case, the probability of the negative binomial random variable is going to be small. And the idea behind this is, since L is small, there's only going to be a few geometric variables in the sum of the negative binomial, so that means that the negative binomial variable can't be very large. And that's how we're going to be able to sum over all of the values of L. So we get that for a particular I bigger than a constant times n, and any particular L, the probability there's an I active L sequence is small. So then we're going to sum over values of L. There are only n of them. The next thing that we're going to do is sum over values of I that are bigger than a constant of times n. There are infinitely many such values of I, but the probability is exponentially small. So that's how we get our final lemma that shows that the probability that there's a omega n active sequence is polynomially small in n. And this concludes the final step of the delay sequence argument. So let's go over the argument again. We identified the objects called delay sequences. These were these paths that we saw. Then we defined the notion of an I-active delay sequence that had several criterion of probabilistic events that must happen. Then we argued that a process ending in round j creates a j-active sequence. And we showed that the probability that there exists an omega t of n active sequence is small. And this, of course, lets us conclude that the process ends quickly with high probability. And that's the final theorem of the paper, that the graph coupon collector process we analyzed has linear cover time with high probability. So let's see a summary of what we saw in today's talk. First of all, remember that our argument uses the delay sequence structure, which lets us get the result without using any graph structure except the degree bounds. Our upper bounds match Alon's lower bounds on the cover time for this process. And of course you can find a number of other results in the paper. For example, you can find an analysis of this process on directed graphs. You can find an analysis of various variants of the graph coupon collector process, because remember at the beginning I said the way in which you choose which uncovered neighbor to cover leads to different variants. And you can also find analysis of the methods of selecting an uncovered neighbor. So in other words, we show that under some methods of selecting an uncovered neighbor, you don't get this nice linear cover time. Thank you very much for listening.